Bonjour, this is Masfin Tawalda, and this is just to show you the steps how to run a Hec-Ras model using a real data in using a real data of a river called Air, which is located in Geneva. So let's start. This is Hec-Ras model. Okay. This is a bit different from the previous one because the file format is different. That's not in Excel, it is in Hec-Ras model itself. So let us first unit system is okay, international. Then open a new project. Let's call that new project La Air. They call it La Air. So La Air. Okay. So we have created a project. Now we need the data. Yeah, the data is, geometrical data and also hydrological data. First, let us import the hydrologic data. Here it is. We can import it from here. Okay, it's here. Okay. Then SI unit finished importing. So we have imported the data. This is just the plan of the river. You can see the first segment of the river will pass through a tunnel, and the other part of the river is just normal natural river. So it's just a meandering natural river, and the length of it is 5.36 kilometer. So that's it. So we have already imported. We can see some of the this is a cross sections view. Yes, although the cross section need a bit of modification. It means we need all the correction, this the levies and also the bank stations must be in order. And the other thing which we have to consider is that you can see, we can zoom it. You see, for example, here is the cross section, and there are bridges along the cross section also. But you can see some of the cross section lines cut the river 3 or 2 times. You see, you can see, for example, here this cross section cut the river 3 times. It cuts 3 times. One here, the other 2 here, here 2 second, and the third one here. So this implies that the cross section is intended to be here. The cross section represent here the section of this part of the river. So it's wrong to have the cross section of this one and this one by the side of this one, because Hec-Ras assumes that it is just like they are in the same plane um, and by the side of each other, and whenever the river you see becomes full, um, the overtopping flood may go to the other one, or also the Hec-Ras assume also whenever the water level in one of the river channel is has a certain level, then it also share into the other part of the channel also. But it is impossible, practically it is impossible to connect this part of the river with this one. It means they are very apart, and also water can't come to the upstream side, you see. It's very difficult. So we have to indicate this in the software. For example, we can see 4132, see in the cross sections, yeah, we can see 4132, 413282. You can see here, see, this one is a real river, but we have this cross sections, you see. So when the software calculates, when the level reach to this level, then it will also fill this one as well. But in reality, this doesn't exist, or it will be wrong anyway. So we have to do something. For example, we have to use this levy to inform to the software that uh, the water must not go, can't overtop this one. And also there is another way of telling add block ineffective areas, like we add ineffective areas like this. So this one is ineffective, you see. Although when the water fills up to this level or above the height of this thing, the elevation of this ineffective area line, then it may use again this place, this canal as a flowing as a stream, but we can make this one permanent, so it will never ever fill. This is one information I have to give. And the other is that let us see, I mean, the tunnel part, you see, has some leads, so we need to put leads. This means this is a superstructure which covers the tunnel part of the river, so we have to put a structure here so that the software understand the height and everything, you see. It's just an information. And to put leads, you can add leads, and you see, just check the elevations. If you make this elevation 4, for example, it will change. You see, it's up on. So we just give maximum and minimum and the station point, so it will create for us by itself. The other is horizontal variation in value. The variation in value, if you click this thing out, you see it's all the n values disappeared. So it generally gives n value 0 0.2 for left bank and O bank. So it is advantageous to put this thing, because whenever you put this 0 0.0 to here, the consecutive points also assume the same value, and also this one. So it will be okay to put like this. So as the other thing, and obstructions also. There is also obstruction in this tunnel somewhere else. Mm, see, so we have to tell to the. You see, this is an obstruction. This is it's obstruction. It's just a block, section that is blocked for to a certain level. So we have to inform to the software that there is an obstruction. You see, so we just assume we put this thing. It's very simple, the same as the leads. So that's it. This is the information we have for the cross sections, and also always the cross section need to have, for example, this point, the stations needs to be moved to a point where the bank stations are. You see, like this. You see, this is a bank station. If we assume this is a bank station, we can put this one as a bank station, and this one we have to move it to here. This, because these are levees. Levees are, you see, water can't flow above levees, so that's levees. For another other cross section, we can see, you see, we can put, for example, this levees like this, and also the ineffective area tools also can be used also. These are the banks to indicate the bank is good, because later it tells that whenever there is overtopping, so we automatically understand there will be a danger, inundation. So if there are structures along the side of the river, then those structures must be considered in a design, you see. So these are the most important parts in dealing with this, with the cross sections. So um, so um, that's all. That's all. We can run the software after adjusting each point of each cross section. The cross section, you see, you can see a lot of cross sections here, around 200 cross sections. So each of them needs to be adjusted. You see the bank station, the levees, and so on. And also the other is, in the tunnel it is very difficult to survey. So there is a need to have other matter of putting many cross sections in the tunnel part. For example, by taking in meters or using GPS and so on, we can take 2 points and we can interpolate the other part of the tunnel from those pointers which we have measured. You see, so the asterisks here indicate that the interpolation, that is a value interpolated, it means. So that's it. It is easy to interpolate between 2 pointers. For example, we can do interpolation here like this, between two axis cross section, for example, between 500, between this station and the next station is 5313.66. Their distance is 25. If you want to have a 10 meter distance cross section, then we can put 10 and just interpolate. So we have now 4 cross section along the ridge. So that's how we can interpolate between two surveyed stations. The other thing is, no, there is nothing important now to run this model. So we need the bridge. Okay, we need those bridges must be in a proper order. For example, the decks, you see, we need the decks. The high chord is the top part of the deck, and the low chord is this the lower part of the deck. It's very important to put all these things into the river, because whenever the flood or the level of the flood becomes above the low chord of the deck, the bridge, then it assumes a weir flow, you see. So it uses weir flow calculations. So we have to put some of the, for example, minimum weir flow is this one. So this is 389.98, I think. So the type of the weir is weir crust shape is broad crusted, because the deck of bridge is broad crested. The width is 5 and weir coefficient is 2.6. Minimum is, it is preferable to use. Then this is 0.1. It means the distance between the cross section which is found immediate upstream of the cross section. So that is mostly, it is 1 meter, something like that, but it depends upon the distance which you put. So 0.1 is 10 centimeter, it means. So it means there is another cross section which is 10 centimeter above the bridge. Yeah, so that's all. This is the bridge. If you want to have piers in the bridge, you can put piers also here. For example, you can take a deck elevation 392. Let me take this is 392, and the lower one is 389. So we can put 389 and 3. How much it was? 392. 392. And the pier width 1.25. Let it be like that. Then 1.25 if the widths of the weir are the same from the bottom up to the top. Then if the downstream side of the pier is also similar, then copy, and then we can put the pier in center line station, because you see this is a negative, the left side is negative and positive. They just did the cross section as center line is 0, so we can put as 0, we can say 0 0. Okay, we have a pier, you can say the mean, you see. Yeah, we have a pier, you see. We can put a pier, but because we decreased some points here, it just there is a gap here, but we can make it up to the bottom of the deck, so it's possible. If we have sloping abutment, the sloping abutment is an abutment which is formed by the side of the two um, the the bridge sides, you see, left and right side. So that is an abutment. If we have an abutment, we can put it. So if you don't have, we don't have. Say in this case, we don't have an abutment, but it is the same as we did to the piers. We can put length, elevation, something like that, and the station points. If we have a culvert, we also put culvert. We just give a station and whole diameters and so on, and edge parameters. This is just a storage elevation curve. So if we need to have a storage elevation curve at the bridge, we can put that thing. So we have almost 5 bridges along the along the river, along the segment. You see, we are considering that is the river air. um, that's it. So we can now continue. We have to save everything, you see, after correcting everything, and we put geometry of air. We can put a name, can give a name, and yes, it's finished. Now we have finished. Now we need what? We need hydrological data. For the hydrological data, we can see we have hydrological data. See in a recurrence interval, you see, for example, a 10-year recurrence interval, 30 year, and 100 and 300 years. So David Crew Sentinels, tricentenals, it means Q's 300, and David Crew Sentinel means 100 years, it means trentenal, and this decennial is 10. So you see, along the river there is a construction, and before the construction, it means avant troisième étape means before the construction, and après troisième étape. So after the construction, let us see after the construction. After they constructed a diversion structure, I will show you in a moment, in a photo or in a video, um, the area where they are constructing and what they are doing. So um, we will come to that, but this is the discharge that is calculated at a certain point. For example, at the Autoroute bridge, it is 63. They have recorded it for many years, so it is also possible to just calculate using a runoff. It's a calculation. This is catchment studies. You see curve number and so on. But in Switzerland, they just do measure each day, automatic, manual, everything. So it's sure that you can take from the data, recorded data as well. So it's 33 for Pont de Marais, and Pont Rouge also 42. That is for Q10. So 5 kilometers is around Pont de Marais. So we will take 33 and 42. It means 33. If it is 33 at Pont de Marais, there is an augmentation. There is an increase at Pont Rouge. We'll see where Pont Rouge is. Pont Rouge is just as the tunnel, it's just an entrance to the tunnel. So at just around the entrance to the tunnel, the the flood will increase into 42 meter cube per second. Um, it was 33 before at the Pont de Marais because of the tributaries, affluences, and other additional flows. It increases to 42. It's obvious. Then 36 après troisième étape, it becomes 36. 45, then the 30 is Q30, the other Q39, Q4, I mean Q139, and Q100 again at Pont Rouge 48. Here 46 and 40, 56 is maximum at Pont Rouge for 300 years of recurrence interval. So we will see whether the the tunnel will accommodate or not for the 56 meter cube per second discharge. So we'll see. Okay, that's all about. So now before we're going to do the adding hydrological data, it's better to have to take some geometry. I mean, corrected geometry from other five, which I have done before. So let me close this one and add data which I have done before. Okay, let me exit. Okay, open a project. That project is, yes, just put it in here in the desktop. This is apparatus, after the construction of apparatus. It means after the construction of the third step of water structure. As you see now, I've already put the hydrological data. I can show hydrology. You see, at point Demaris 5,363.91 kilometer meter. The discharge are already entered. This is very simple. You can put this source for 34 or 33. Just click and put the data. And here also we can click, and for the first point we can add a flow change location. We can add one, and it will make you see, for example, you can add, for example, we can add, let us add one another, put add. You see, I have already add one, and if we don't want it, we can delete it out. Yeah. Let me delete. See, I can delete that one. Yeah. Delete row from the table. I can delete this one. So it's already deleted. Now we put 4 because we have 4 types of recurrence intervals. That means for Q10, Q13, and so on, QNCC100. That is a name. We can change the names, just edit profile name and change these names like this. So it's very easy. We can see the previous video that shows every step. And reach boundary condition is now for a normal depth. We just click here and put the slope of energy line, grid line. The slope is realistic 0.042. We can take the slope from the ground surface, that is vertical increase to horizontal increase. The deviation point are two different point. I mean, the distance, horizontal distance, and the difference in elevation will give the slope. We can take average slopes, so it's realistic. You see, in a natural river, most rivers do have very low slope value, because natural rivers are always becoming stable. See, they are always striving to become stable. It means uh, they keep um, themselves in a balanced state. For example, you can see if the water flows in an area where very big big or wide surface area, then the flow decreases and the velocity decreases. That means because of the decrease in velocity, some of the sediment which is carried from the upstream will be dumped to this area, because the flow is less and the water flows gently. Then through long process, then those dumped sediment used to make this side bank and so on, and it becomes slowly narrower and narrower. Then um, it until it forms a velocity called an unscouring and non-silting velocity. So as the same, when there is a narrower surface area, um, or river channel for the discharge, the discharge also, because of the narrow space, the velocity increases, and through time it erodes some of the parts of the berm or the banks. Then slowly it becomes wider until the velocity becomes an unscouring and unsilting velocity. This is very, very interesting for natural rivers, and nature is intelligent. They are just themselves, so they are always imbalanced. Because of this, the slope is always a very, very gentle slope. That is, the slope itself is a non-scouring and non-silting slope that supports the velocity as well. So most of the rivers in irrigation canals, in designing irrigation canals, the slope is very, very low, 0.025, 0.05, something like that. So we are in a range that is acceptable for the natural river, so it's okay. And we put click here, we click here and put, then okay. Then after that we click apply data, and then save the plan. We save the plan with flow data. Okay, now we have saved the flow data apparatus step. We have downstream is the project name, and we have the geometry air2, that is which I have taken before, and this one is a steady flow apparatus step for calculation the steady flow. We can calculate now, because we have already, first of all we have to create open a plan, and then we save it. You see, we open a plan and save, so that let's compute now. It's already, because we have done everything. Okay, now we are successful in our computation. If there is something wrong in our calculation, or if there is any problem in the cross section and so on, it will stop us. But we are now fine. It's fine, so we can save our plan and finish our calculation. So as a final step is the looking at the cross section, at the longitudinal section. You can see five of the bridge and the tunnel also, and we can see at the 100, for example, at Q300, Q300, still the flood can pass through the tunnel. So it is very successful project, because 56 is accommodated in the tunnel. So if it is beyond 56, it means, for example, 60, 70 or something like that, it has to be diverted. It must be diverted by any means, otherwise it will overtop here, and it is a city around here, a village, Petit Lancy, I think. So this part of the village will be inundated. It's very difficult. So this is now a success. Is very good. So we are sure that we don't have any problem in the future. As far as we have an upstream mechanism to decrease the flow, or create a temporary detention dam. You see, we can create a temporary detention dam or a diversion. I can show the diversion they did. Okay, let me put here, for example, here these are the pictures. Okay, this is just a picture which I have taken um, after a rainy day. You see, you can see damage, some damage. You can see here the structure. Okay, they have done a structure. This is the outer route where the discharge is 60. So we are calculating below the this one. So you see, this is a water structure. This is the natural flow of the river. Here the water flows this way. Whenever the amount of discharge is more than the capacity of this natural canal, it goes, or it flows over the weir, and it will be diverted, and diverted and we'll go to a river called Arv. See, we'll see that in a moment. This is the structure. You see in Hec-Ras the build structure. This is called a biological method of stabilizing a berm. So it's very interesting to have. This is just simply a tissue, and it will be, it's just for temporary stabilizing the plants and then so on. After that, it has no further use. The plant themselves will take care of the berm. Yeah, this one is, you see the river. We can see like this. This is the outer roots, below the outer roots. Okay, this is above the outer roots. Okay, this is a bridge, newly constructed bridge. This is the outer roots. Yeah, regional de la air troisième tapila. Tronçon avant Pont de Lul, Pont de Mare. Yeah. Okay. Okay, this is a diversion. This one is an old diversion. Now it is almost filled by a sediment, but this one is a new one. They built a tunnel to the Arv. This is an Ojai type of weir. You see, this is the old diversion structure. It comes through this and it goes like that. I think they have done this was old natural river channel, but they diverted artificially. They created another channel so that it will be good for them to make another tunnel. I think this one is the tunnel itself. You see, this is the tunnel structure. Yeah, this is the natural river itself. It comes like this and it goes like this. Yeah, so we are considering below this um, this place. Okay, that's all. Um, some of the river we can see. Um, we can see, for example, Pont Rouge. Pont Rouge is here, for example. We can see. You see, this is a petty landscape. If the flood field, I mean, if the discharge amount of the coming flood is more than 56, for example, it will increase. You see, it will inundate this area. It means, so it's very difficult. This is Pont Rouge, and yeah, these are some of the. This is a photo which has been taken after a rainy day. This is Point Centenaire. Point Centenaire. See, this is Schema du Pont du Centenaire. So Point du Centenaire is the name of this bridge. So we did our calculation below this level. You see. Yeah, yeah, yeah. These are some of gabion structure. It's an old gabion structure. You see, most of the time rivers, you see, when they just make a curve, they erode the curved part of the river and accumulate the inside part of the curve. You see, the one which is the convex part. They just erode the concave part into the convex part. You see, so because of the vortex movement of the flow, you see the sediment eroded from one side into the other side. This is happens in natural rivers, so it's good to have protection like this gabion. You see, um, they have also this is, yeah, This is the naturally the river banks covered with a forest. So you can see how we chose to have n value 0.14 the banks, and for the riverbed we have taken 0.05. Mm. Yeah, this is you see a damaged bank, so it's always like that. There is, oh, you see, because of the nature of the river, they erode this part and accumulate to this side. It's always like that. The curve is going like this, the convex part, you see, and this is the convex part. Oh, no, no, no. They have to, they erode from this side and accumulate this side. Actually, this one is, the upstream side is like this, so you can see, yeah, yes, you see. They erode from this side and accumulate this one. So this is the upstream side of the node. So it eroded a tree, and you can see this part of the bank is still vulnerable to more erosion, and it needs to be protected. Yeah, yeah, that's because if it is not protected, it will make a lot of damage. It may even change the route of the river as well. We can see other protection like this one, for example. This is you can see this protection. You see, this is another biological way of protecting the river. I see here you can see it is they have already built wood structure here, because when the water comes here, you see this curve, you see concave curve, it makes a vortex movement so that the water will store here. The sediment will store more sediment, store here, eroded from here, store here, eroded from here, store here. So through time the river might change its course like this, and it may damage this tree, and there is an asphalted route here. It will be dangerous for the route itself. So instead, what we have to do is protect this side, this curve, with a structure. This is cheap because of this naturally available. Instead of using cement and other expensive things, it would be preferable to use some woods and so on. So this is all about the river, and the our calculation results. We can see some of our calculation results like this. This is the plan of the river, and for the 300 it means, for, see, you can see the profiles. Yeah, for all of them actually, but we can clear here and put only for 300 just to see. For 300 you can see Q300, you can see some of the areas are widely affected. Some of the area has, because of the levees, it's protected even if the flood increases, but there are some areas where the banks are very low, so that the flood can overtop, you see, and affect the surrounding area. If there is um, some, okay, we can put this thing, no, no, okay, okay. You can see here, this is the levies and bank stations, so you can see clearly now this part and this part and this part are inundated. So it's very very important to take care all these areas, and take some measures. That is the recommendations I have. So that's all about the running Hec-Ras model in inlet, yeah, the river air. The other important aspect of river air, we can see some of, for example, the the catchment area. For example, this is a catchment area of air. The river comes from its tributaries from France, and then the red point, that is Geneva. It's a territory of Geneva, and it flows down to the city, center city, to Confignon, Lancy, and so on. And as you see, there is a structure here, that the one which we saw. This is a tunnel to reduce the size of the flood, which is flowing directly into the river Arve. So by reducing, you see, they divert here some of the flood into directly into the river through a tunnel, through that Ojai um, weir. And these are some other flows like sewerage and so on, which mix to the to with the river. So these are the explanation about the river, and this is the point where the Pont Rouge is located, and after that it becomes so you can see the dotted indicates that it is a tunnel underground. um, the other is that which I want to show is you can pick some of the you can pick some of um, the n values from a table. You can see th these are in French, but you can see item 4 is similar to 4 avec pièce with a stone. So we chose 0.1 and n value. K means 1 over n. It means K is length of the roughness, the height of the roughness, the measurement, you see in micromillimeter or something. So 1 over K gives you an n value. That's all about. We can choose K, we can take directly K or n also. So it's possible to take both. For this is for natural water, and this one is for artificial canals. So yeah, this is how we chose the that's separate. You see, for the banks are full of trees, and the riverbed is just like it's a boulders. You see, very small boulders. So that's why the n value is low, 0.5. The other is maybe the um, also I think that's all. We can see the video from the online, also the video of the river itself. So that's all. Merci for thank you for listening, and I think it is profitable. So I hope we'll come some other time with another problems also. Thank you. Cheers.